In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave. But then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it which appears to travel backwards in time.
The experiment begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through, and because we have no measuring device at either slit, we cannot know which slit the laser fires through until they pass through and are detected on the other side. So at each firing, it will either go through A or B. Now the first prism splits the entangled photon.
This is how it works. When two subatomic particles interact, they can become entangled. That means their spin, position, or other properties become linked through a process unknown to modern science.
If you then make a measurement of one of the particles, then that instantaneously determines what the behavior of the other particle should be. And when the experiment is done, it's found that indeed the other particle's quantum state is exactly determined once you've made a measurement of the partner particle's quantum state.
Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern, if it only came here. If we could place a measuring device at the slit, we would know the path information. But with just a result from D0, we don't know the path information. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both, becoming the wave of possibilities it could have been, instead of one of these possibilities, if we knew the definite path information. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now if the photon hits either one of these detectors, notice what happens. We obtain which path information, because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. There is no way a photon that came out of B could hit D4, and vice versa. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1 or D2, it could either have come from A or B. We can't ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern, demonstrating the photon went through both slits, since we don't have definite path information. Now here is one of the important implications of this experiment about what is causing collapse. Some argue physical interaction from the detector is what is causing the collapse, but if that was the case, D1 and D2 should cause collapse every time. But that is not what happens. If a photon makes it to D1 or D2, they always display an interference pattern. Yet every time a photon hits D3 or D4, a clump pattern is formed. But the only difference is what we, the observers, know about these two stations. Because of the experiment setup, we know that if a photon hits D3, it will always be a clump pattern, showing the photon only went through one slit. If it hits D1, we know it will always be an interference pattern, showing that the photon acted in a way as if it went through both slits. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that is not what the experiment shows. We always get a clump pattern at D3 and D4 because whenever a photon hits here, we always know the path information. And we always will get an interference pattern at D1 and D2 because we can never know the actual path information. So the photon acts in a way as if it goes through both. Whereas at D3 and D4, the photon only goes through one slit because we know the path information. The particles act in a way that correlates to our knowledge. See, what causes collapse is knowledge, and knowledge requires a knower. Sir Rudolph Peirce said, "The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result." You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows. Now the other implication is even more mind-boggling, because the photon knew beforehand where it would end up. How do we know this? Because of how its twin acts at D0. The twin photon registers at D0 before its entangled twin ends up at a detector, and whatever registers at D0 always correlates to wherever its twin ends up. So if the twin hits D3 or D4, D0 always registers a clump pattern to correlate, and always an interference pattern if its twin lands at D1 or D2.
I don't understand it. I don't know that anyone does.